So good afternoon, class. Right. So I hope you are doing well. This week's tutorial is actually based on feedback amplifiers. In this particular week's tutorial, we'll be basically identifying the beta and the alpha circuits from the circuits given, and we'll also try to identify the topologies. Right. So we have basically one question for this week's tutorial, right? But that is broken down into two parts over here. So let's begin with this week's tutorial, right? Please keep and just before we start, just a reminder, please keep your queries till the end of the class, right? So when we finish with the discussion of this tutorial, then you can start raising your queries, right? I'll be looking at your queries at the end of this particular class because it's one question. So we'll finish this one question and then I'll be looking at your queries, right? So let's get started. Question number one, it says, for each of the op-amp based circuits shown in figure below, A, identify the feedback topology and indicate the output variable being sampled and the feedback signal. So basically we have to identify the feedback signal, the output variable and the feedback topology, and B, find the expression for only beta, right? Or the feedback factor. So there's four circuits over here, right? So let's quickly identify the topologies for all of this, right? So in this particular case, you can see the feedback network is actually in series over here. In the input, it is in series. And at the output is across this RL circuit, right? So your output is over here. If I draw the point over here, let's say, the output is at this particular point. So you can see that the feedback network, this is your feedback network, is actually in shunt with your Vout, right? Okay. So what happens is your input is in series, your output is shunt. So this is the topology of this particular network over here that is given. This particular circuit is series shunt, right? So the solution for this, or the topology identified, is series shunt. The input is a voltage source, right? The input is a voltage source. The output is voltage Vout, right? Because we are basically measuring if the feedback is shunt to the output, right? If it's a series shunt, we are actually inputting mixing voltage, and we are sampling voltage out, right? So that means our feedback over here, right? The feedback over here, this is the feedback that will be given back. That will be basically VF. Okay. Excuse me about that writing, right? So in this particular case, we'll be inputting voltage, we'll be sampling voltage out at the output, and we'll be feeding voltage as well, right? So this particular network is a series shunt network, right? Okay. I'll just say it out. The solutions are at the end, right? So this particular network is a series shunt. Or in place of shunt, I'm going to write parallel, right? So it's a series shunt network or series parallel network, right? So this is a series parallel network or series shunt network. In this particular case, you can see this is your feedback network, right? You do not account your RL as part of your feedback network. So this is my feedback over here, right? You can see this feedback network is actually in shunt, right? It is in shunt with your supply voltage, right? I mean supply current, right? Or supply over here, and it is in parallel to your output. So your parallel will be actually across this RL circuit, and your RL, yeah, if you compare the feedback with your output or at this particular point, this is what we are going to get, right? Vout. Okay, so Vout, if you just draw a line across over here, so you can see that your feedback system is actually in parallel or in shunt with your output. So this particular network becomes a a shunt configuration, right? This particular network becomes shunt configuration because Your feedback is in parallel with your source, and your feedback is in parallel to your output. So part B, you can see it says shunt topology, right? So in this particular case, you'll be supplying a current and you'll be sampling a voltage output. So your feedback over here will be, since you're supplying current, the feedback over here will be also current, right? So your feedback will be current. Then moving on to the C over here. In this particular case, again, you do not consider your RL as part of your beta circuit, right? So your beta network is this much, right? So in this particular case, you can see that your input, right? This particular source over here, this is your input. Your input is actually in series with your beta network, right? You can see this is in series with your beta network, and then right, and your input is actually in series with your load resistance over here, right? So basically, what we'll be sampling is current, right? So your output is I0. That is what we'll be sampling. So in this particular case, it becomes this particular network was a series. Oh, sorry. This particular network was a shunt configuration. So I'll write shunt is also parallel, right? So I'll be writing PP on top over here. P. So this is a parallel or shunt network, right? In this particular case, your input is in series with your beta circuit over here, right? This is your beta circuit. So it is in series with your beta circuit. So your input is in series and your output is again in series with your load resistance over here, or your output, right? So your output is going to be I0. So usually what I'll suggest is the variable that we'll be measuring will be associated to your load resistance, right? Load resistance is where your output will be. So if your load resistance is in series with a beta network, you'll be basically sampling I0. If your load resistance is in parallel with your output, you'll be basically measuring V out, right? So you can see over here in this particular case, your RL was in parallel to your beta circuit, so you'll be basically measuring V out. In this case, again, your RL was in parallel to your beta circuit, so you're measuring V out, right? So in this particular case, your RL circuit is in series with the beta network, so you will be measuring I0 over here, right? So your input is in series with your beta circuit, and your output is also in series with your beta circuit, right? So this is a series configuration. In this particular case, again, this is what you have. So you can see at this particular point, this is where the feedback happens, right? So you can see, since we have a junction over here, your supply current is actually in parallel to your beta network, right? And your output is actually in series with your output. With your beta circuit. So the configuration over here becomes shunt, right? Your input is shunt, right? So that is parallel, right? So your input is in shunt and your output is in series. So it becomes a shunt series. So going back to the solution, the first circuit is series parallel, right? The first circuit is series parallel. The second circuit is parallel. Next one is series, and then we have parallel series. So let's see if we have that solution over here. Series shunt, right? Or series parallel. The first one is series parallel or series shunt. That is what we have over here. For part B, we have shunt, right? So it becomes parallel. That is what we have, right? Shunt. For part C, it is a series network. Part C, it is a series network, right? Topology. And then for part D, it is a parallel series, so it is a shunt series, right? So for part D, we have the shunt series topology over here that we have, right? Okay, so that's regarding identifying the topology. So in this particular case, will be the feedback over here will be voltage, right? The feedback variable over here will be voltage. The feedback variable in this one will be current, right? So we will be basically mixing current over here. In this particular topology, your feedback will be V out. feedback voltage. Voltage will be the variable. In this particular case, the feedback variable will be current, right? So your feedback basically is associated to your supply, right? So whatever variable you have is a supply, that will be your feedback, right? Because you cannot directly mix a current with voltage, right? So that is why when you are mixing or you are feeding something, so you have to feed it with the same thing, right? So you can only mix voltage with voltage and current with current, right? So once we have identified the topology, right? So we have basically identified topology. We have indicated the output variables. In this particular case, it was also I0, right? So we have identified the output variable, we have identified the feedback topology, and we have also identified the feedback signal. So in this particular case, like I said, your feedback will already depend on your input variable. So in this particular case, you're inputting voltage, so your feedback voltage will be also, your feedback will also be voltage. So in this particular case, you're supplying current, so your feedback will also be current. You're supplying voltage, so the feedback will be in terms of voltage, right? Same goes over here. You're supplying current, so your feedback will be in terms of current. Now, going back to the alpha circuit, right? The alpha circuit will be basically equivalent to, okay, so we have basically identified the feedback circuits, right? These are my feedback circuits. So your feedback VF will be at this particular point, right? This is where you feed in. In this particular case, your feedback will be at this particular point, right? And in this particular case, your feedback will be at this particular juncture. And then your feedback in this particular case will be over here. So this becomes your beta circuits, right? So your IF will be here, your IF will be over here, your VF will be at this particular point, and your VF will be at this particular point, because these are from where the variables get inputted to your op-amp, right? So that is regarding the beta circuits. So beta circuits have been identified over here in this particular case. How do you identify the alpha circuit, right? That's the important part. So you can see this particular circuit, right? In the same particular circuit, you can see there will be, how do you, so how do you identify the alpha circuit? So what you do is, for your input part, you break it from the output and you ground it. Break it from the output, you ground this, or whatever you have, whatever connections you have to your output, just forget about the RL circuit. Whatever connection you have to your output, you'll break it and you'll ground it, right? And for your output resistance, whatever connections you have to your input, you break it and ground it, right? So in this particular case, in this situation, if you break for your input resistance for alpha circuit, right? Or what we say is open loop circuit, what we do is we break this particular point over here, right? If you break this particular point, what happens, this R2 becomes grounded. So your input will be basically your supply voltage that is the supply, and we have two resistance in parallel to each other, right? So that is what we have over here. You can see the supply voltage is as it is, right? It is connected to the positive terminal, and your R1 and R2 are in parallel, because your R1 is already parallel. Your R1 is already is actually already in terms of your R1 is already grounded, and then when you break at the output point, your R2 is actually connected to your output point, right? So when you break that and ground it, it becomes something like this, right? So your input resistance becomes R1 in parallel with your R2. Now, like I said, that was regarding your input side. Now, regarding your output side, because remember, your your alpha circuit is actually an open loop circuit, right? You cannot connect it in the feedback. So in that particular case, what you do is you disconnect the feedback, right? So in this particular case, your feedback is at this particular point. So you break the circuit at the feedback point, right? Your feedback is at this particular point, break it, and you ground the circuit. So in this particular case, you leave the connection with your output, right? So if you break the circuit at this particular point and ground it, so what happens is that this R2 becomes in parallel to your RL, right? And then this R1 can be ignored, right? So that will be the resistance at the input. So that is what we have. R2 is in parallel with your load resistance. So this becomes your alpha circuit or A circuit, that is your open loop again. So remember, when you look at the input side, right, input to the op-amp, since it's an open loop circuit, you have to break it at the output point. So if your resistance, whatever resistance is connected to your output, you break it and ground it. So that becomes your input circuit, right? Your input resistance, right, to the open loop circuit. That is what we have over here. And then your output, for the output, you break it at the feedback point, right? So your feedback is at this particular point, you break it at that particular point because we do not want any feedback, right? In an open loop circuit, there is no feedback. So we break it at this particular point, and then we ground it. So if you break this circuit at this particular point, what happens is this R1 becomes, is not associated with your V out, right? And we are just looking at towards your output, output resistance, right? So in that particular case, your R2 becomes grounded, right? And that will be in parallel to your RL. And that is the alpha circuit that we have over here, right? Okay. And then regarding the beta circuit, like I showed you, your beta circuit is this circuit over here, right? So your input to your beta circuit will be V out, right? And your output will be VF, right? So that is what we have. R1 is in series with your R2, right? Yeah, R1 is grounded, then you have R2, and this is where we have our V out, right? And this is the point where we have the VF. Okay. So let's ignore this. This is incorrect actually, right? This is the symbol that we should be having, right? So your feedback is at this particular point, right? In between R2 and R1 is your feedback point, right? So that is what we have, right? In between R2 and R1, you have the feedback point, and the output is after R2. So after R2, that is what we have. So the beta circuit, this is the beta circuit we have. Your input to this particular beta circuit is V out, your output is VF. So writing the beta gain for this particular circuit, right? Or the what do you say, the feedback factor, right? Beta. Finding the feedback factor, beta is going to be just a simple one. You can say you are supplying V out and then you are sampling VF, and VF is basically since R1 is grounded, right? R1 is grounded based on this particular circuit over here. R1 is actually grounded. So you can see if we are taking VF at this particular point, it is the voltage across R1, isn't it? So basically, in order to find beta, we can use voltage. We can use voltage ratio, right? Or voltage division to find the voltage across R1. That will be our feedback, right? VF. So VF is basically equal to V naught, right? VF is basically equal to, wait, let me write it over here. That will be much easier. VF, if I write the equation for this particular terminal, it will be VF is equal to V out, right? This is V out, which V out times R1, since we're going to, VF is the voltage across R1, so we can use the ratio. So that will be R1 upon the total resistance R1 plus R2. Right, so that is the equation for VF, and then your input is V out, right, and your feedback output to the beta circuit is VF. So finding input output upon input, right? So VF upon V naught. So VF upon V naught will be your beta gain, right? So making taking this V naught to the other side, that will be equivalent to our beta. So beta is basically equivalent to VF upon V naught, right? Which is equal to, right? If you take this V naught to the other side, you'll be just left with R1 upon R1 plus R2. So that is what we have. And that becomes your beta gain, right? Okay. So basically your beta is equivalent to R1 upon R1 plus R2, right? So the others were, you can see the supply was in series shunt network. So in this particular case, the topology was series shunt. So basically we are sampling voltage, right, at the output, and we are mixing voltage at the input, right? So that's regarding this particular question, right? And then if you have to find the feedback gain, or the close, I mean, not the feedback gain, sorry, the closed loop gain of this particular circuit, it would have been V out upon Vs. That is basically equivalent to alpha upon 1 plus AB or alpha beta. That is equivalent to, we can assume that the gain of circuit A, right? This open loop gain as mu, right? So let's say if the gain of A is mu, right? Some variable mu, that is what we do. So in place of A, we substitute mu, and in place of beta, we substitute R1 upon R1 plus R2. So this will be the formula for your closed loop gain, right? So we went to find the closed loop gain. However, this is shown over here in your solution set, right? And this is where you get your A is equal to basically your mu, right? So your open loop circuit could be considered, I mean, your open loop gain could be considered some variable mu, right? So this is what you have, right? So we have basically identified the beta, right? That was told to us to be identified in part B, right? The other parts are just simplification, or the other way of reading this is 1 upon beta is basically equivalent to R1 plus R2 upon R1. So that was regarding part A of this particular question. Moving on to part B. For part B, again, we have already identified the beta circuit. So this is the beta circuit. However, for the alpha circuit, remember, like I said, for your input circuit, right, your input will remain as it is, right? So in this particular case, if you are having a supply and this particular terminal is grounded, that is fine. It is only at this particular input part. So how do you go about taking this? So like I said, if you are to look, I mean, for an open loop circuit, what you do is just look at the input side, right? So input sides are this positive and negative sides. So what you do is break any connections to your output. So any connections to your output at this particular point is just R2, right? This is the connection that connects the input to the output, right? So we break it at this particular point and then we ground it. So if we break the circuit at this particular point and ground it, so it will be just the supply voltage in parallel to your R2, right? And your positive terminal is basically grounded. So let's see, you can see your supply current is actually in parallel to your R2 because we have broken the connection, since R2 is the connection that connects the input to your output, right? So that is where we break the circuit at the output and we ground it, right? So if we break it at this particular point and we ground it, so this is what we get, right? That is your input resistance. Now looking at your output resistance, right? Now I mean, this op-amp has an input and output. So then we look at the output side. So at the output side, what happens is any circuit that connects to your input, we break it at the feedback point, right? So in this particular point, yeah, this is again the R2 that is connecting the V out to the V in, right? So what we do is we break it at the feedback point, right? At this particular point. So if we break it at that particular point, you can see your RL becomes in parallel with your R2, right? So your output, then the output resistance then becomes, sorry for this, your R2 becomes in parallel to your RL, right? Again, the beta circuit, right? This is just the beta circuit. So we have an output and then we have a feedback, IF, right? So this is the beta circuit, just R2, right? So what happens is your input to the circuit will be V0, your output will be IF, right? So your beta formula is basically IF upon V0, right? So if you want to find, if you find, so like I was saying, right? So this is what you have for your beta circuit. Then what happens is that if you find the your input, so basically if you write the formula for IF is going to be basically V0 divided by R is equal to IF. Remember your IF should be in this particular direction, right? however it is flowing in this particular direction. Okay, let's just consider your IF to be in this particular direction because your feedback is coming in this particular direction, right, from your V out. So in this particular case, since it's a shunt topology, so your output becomes your input to the circuit or to the beta circuit, right? So basically your current, let's assume that your current is flowing in this particular direction, right? In anti-clockwise direction, right? In this particular direction, right? So what happens is your IF is basically equal to V naught upon R. So if you make, since we know that beta is equivalent to, in this particular case, the output of this particular circuit is going to be IF. So beta is equal to output upon input. So IF upon V naught, right? So that equates to, that would equate to making, I mean, IF divided by V naught is going to be equivalent to just 1 upon R, right? Rearranging this formula in this particular form, that is IF upon V naught, right? So we get 1 upon R. Now, what you can see is that the input is basically supplied to the, or the feedback is basically, the input, the supply is basically inputted at the negative end. So your output will be inverted, isn't it? So what that indicates is your IF upon V naught will be basically negative 1 upon R. Okay, so your IF becomes negative. Remember that, right? So that becomes IF upon V naught is equal to 1 upon R. That is what we got. And then we have to ensure that your IF, your V out is actually, your supply voltage is actually connected to the negative terminal. So that is where we get the negative from, right? So in that particular case, your beta becomes negative 1 upon R because your supply is connected to the negative terminal. So your output will be inverted, isn't it? So this negative basically indicates inversion, right? Or your output is basically inverted. So that is how we come to IF upon V naught is equal to negative 1 upon R, right? So it's not R, actually it's labeled as R2. So ignore that, right? So this is basically R2, right? This is R2. So your beta becomes IF upon V naught, which is equal to negative 1 upon R2. And then the gain for your open loop circuit in this particular case will be your alpha value is basically equivalent to, so A is V out upon IS, right? So in this particular case, if you see this particular circuit over here, the open loop circuit that we have, right? So if you are supplying current, right? So there is IS dash, right? Let's say that is the variable associated with the open loop gain, and then it's a shunt, so your output variable is again V naught, right? V naught dash, right? So in that particular case, what happens is that if you do V out dash upon IS dash, what you can see is that IS over here, it will go through an open loop gain through this particular op-amp. So the gain of that particular current will be basically by factor negative mu, right? So if you have a current, if you have an output of negative mu times V1, so in that particular case, you can assume that the negative factor, negative mu, or your V out in that particular case, V out dash is basically equivalent to negative mu times IS dash. So this negative mu is the gain or the factor that is the current across this R2, right? So let's say some factor negative mu, right? Negative is basically, since the IS is actually connected to the negative terminal, so that is where we get the negative from. And then mu is just any factor, right? It can be any factor that we don't know. It's an open loop gain, remember. And then that negative, your V out is basically negative mu times the, okay, let's keep it like this, right? If this is I dash, IS dash, right? So this is your supply current. This is your output voltage, right? So let's say this goes through a open loop gain. Let's say that is some factor, right? Some factor, and then what happens is you can say V naught dash is actually the same same voltage across these two nodes, isn't it? Okay, it is the same voltage across these two nodes, right? So what we can say is, let's say is goes through some gain that is mu, and then that is gets split into two branches, right? So whatever that is split into this particular branch, it goes through this particular branch and this particular branch, right? That could be, let's say, the gain across, like is goes through this particular op amp, and then the gain becomes A times is, right? Example, right? Not A. Let's use some other variable, X, right? So let's say the gain across this particular op amp is X times is. So, and then what happens is that this particular current splits across this particular branch. So then there's another factor, right, that splits this particular current, right, X times is across this particular branch R2 and RL. So let's say that factor is Y. So that means Y is the factor that splits X is into this particular branch. So we have Y times X times is. So what we can do is, we have two unknown variables, X and Y, right? That is the current flowing across R2. So X, Y times is, isn't it? Is the current flowing across this R2. And then the current, I mean, the voltage across R2 is the voltage at this particular node. So that will be multiplied by R2, right? So that means V naught dash is equal to negative X times Y times is dash, right? Times R2. So in this particular case, what we can do is, you know that X and Y are two constants, right? X is the constant for the gain over here across this particular op amp, and then that whatever gain, the current gain that you have that passes through this particular op amp, that is again split into this two particular branch, and that is by a factor Y that is being splitted up between these two particular branch, right? So in that particular case, X and Y is my constant. So what do I do is, that becomes X and Y could be represented by a constant mu. So in that particular case, V naught dash is equal to, right? V naught dash is equal to some factor mu times R2. Okay. So now, I mean, some factor mu times R2 times is dash. Sorry about that, right? So now making V naught dash upon is dash, that is equal to I, we are left with negative mu times R2. So in that particular case, our alpha gain, or the open loop gain, becomes our open loop gain is equal to negative mu times R2. Okay. So that is how we arrive to alpha is equal to negative mu times R2. Negative indicates that the output is inverted, because your input is connected to the negative input, right? And mu is some factor xy, right? Mu times R2. So your open loop gain is equivalent to negative mu times R2, while your beta gain is equal to negative 1 upon R2. So if you are to find your feedback, the closed loop gain, that would be basically equivalent to V naught upon is, right? So V naught upon is basically equivalent to A upon 1 plus AB. So in place of A, that will be negative mu times R2. So negative mu times R2 plus negative mu times R2 times negative 1 upon R2. So mu, I mean, this negative will cancel each other off when we are multiplying. So we will be left with mu R2 upon R2. So mu R2 upon R2. So this R2 and this R2 will cancel off. So the feedback gain is basically equivalent to negative mu times R2 upon 1 plus mu, right? So we do not need to calculate this feedback, the closed loop gain. We were just interested in calculating the beta gains, right? So this is just given over here, because the open loop gain is slightly complex, because you can represent it anyhow at the moment, right? So we have basically, I mean, in this particular case, we have chosen to represent this in terms of R2. You can also represent it in terms of RL as well. It can vary. And then you can also represent, I mean, you can say that there's some factor, I mean, there's some multiplication across this. Okay, yeah, so you get the fair idea that, you know, the open loop gain can be written in multiple ways. So we are just interested in the feedback gain over here, that is -1 upon R2. Moving on to circuit C, right? In circuit C, again, what happens is if we draw the alpha circuit, remember we break the circuit at the output to form the input resistance over here. So if we break the circuit at this particular point, what happens is, so if you break the circuit at this particular point, you can see your R2 becomes in series with R, right? So always remember, if you are breaking, it should be after RL, right? Sorry about that. It should be always after RL. So whenever you break the circuit, it should be after RL and just at the input circuit as well, right? At the feedback point, right? So in this particular case, we need to break the circuit at this particular point. So our input, I mean, the resistance at the input will be this supply voltage will be connected to the positive end, just that this particular beta circuit will now start to hang. So you can see in that particular case, R1 becomes in parallel to R2 plus R, right? Yeah, R2 and R will be in series if you break it at this particular point. So your input resistance in that particular case becomes R2 in series with R, and that is in parallel to your R1, right? And then you go towards your input side, right? So at the input side, what happens is you break the circuit at the feedback point. So if you break the circuit at this particular point, right? If you break it at that particular point, what happens is in that particular case, your R2 becomes in series with R1, and that becomes in parallel to your R. So that is what we have over here, right? Your R2 is in series with R1, and that is in parallel with the small r, and RL will remain as it is, right? So that is regarding the alpha circuit, and this becomes your beta circuit, right? That I have highlighted over here. So the topology that we have identified for this particular circuit is series. So basically, what we are doing is we are mixing voltage and we are sampling current, right? So in this particular case, the beta circuit, right? Remember, your beta circuit is something like this, right? Remember, your feedback voltage is at this particular node point, right? At this particular point, just in between R2 and R1, isn't it? You can see in between your feedback point is just over here. That is being supplied back to the op amp. It is in between R2 and R1, right? So basically your input will be at this particular junction, right? And your feedback will be at this particular junction. So if you draw the beta circuit, you'll get something like this, right? For your beta circuit. Now, as the question told us to identify the beta gain for part B. So beta gain is, in this particular case, what you can see is the voltage is, I mean, the feedback voltage at this particular point is basically the voltage across R1, isn't it? Because R1 is already grounded and this R is also grounded, right? So if you're supplying current over here, so what we can do is we can use current division to find the current over here, right? That will be I1. So we can find I1 at this particular point across this particular branch across R2. And you can see if you ignore this output point, right? If you ignore that point, right? If you ignore that point, you can see R2 is in series with R1. You are just measuring the voltage across this particular point. However, your R2 is in series with R1. So if you find your current across this particular branch, R2 and R1, that will be basically equivalent to, if you use current ratio, that is opposite branch. So if you're finding current in this particular branch, that will be the resistance in the opposite branch. So the opposite branch is here. So I1 is basically equal to I0 times R. The resistance in opposite branch is R on the total resistance, that is R plus R2 plus R1. R plus R1 plus R2, right? So this is what we get over here. Now, if you're to find the voltage across this R1, that means this is the same current flowing across R1, isn't it? So in that particular case, your your VF is basically equivalent to, this is the current, this is the current I1 multiplied by R1, isn't it? So your voltage across R1 is basically equivalent to R1 times I1. So your I1 is basically given by this particular function over here. So I1 times R1. So now if you substitute in place of I1 this whole function, so that will make us make this formula equivalent to R1, right? In place of I1, if you substitute this whole formula, so it will become I0 multiplied by R multiplied by R1 upon the total resistance, right? So in that particular case, that is what you have. And then if you make the subject of the formula, you get, if you make VF, and if you take this I0 to the other side, it will be VF upon I0, right? Okay, this is what you can do. In place of I1, if you substitute the whole formula, you'll be R1 times I0 times R upon R plus R1 plus R2, right? That is where you get your VF from. And then if you rearrange that particular formula in terms of VF upon I0, you'll be basically getting R1 times R, right? R1 times R upon R1 plus R2 plus R, right? So your beta gain is basically this, right? Moving into circuit D. Circuit D is a parallel series circuit or a shunt series network, right? So basically you are mixing current and you're sampling current, right? Okay. So again, in this particular case, you break the circuit just after RL, right? So at this particular point at the output. So this is where your output is connected to. And for your output, if you want to know the output resistance, you break it at the junction over here at the feedback point, right? So in that particular case, the input for the alpha circuit, your input will be, your supply voltage will be in parallel to R2 plus R, right? If you break the circuit, that means your R2 will be in parallel, in series with this small r, and from the output resistance, if you break it over here, your RL is in series with R2 and R, where R2 and R will be in parallel. So if you draw the alpha circuit for this particular circuit or the open loop circuit, you'll get something like this, right? Okay, like I said, if you break it, R2 becomes in series with R, right? And that is in parallel with your IS, right? Where the supply current that you're supplying. And for your output resistance, in that particular case, RL becomes in series with R2 and R, where R2 and R are in parallel. Okay. So this is your alpha circuit, right? And for your beta circuit, we had already identified this is our beta circuit. So your current comes in at this particular point, right? At this particular junction, and your current leaves at this particular junction, right? Or just after R2. So if you draw the beta circuit, you'll get something like this, right? Your current enters just in between our in between R2 and R at this particular junction, right? Right? And your output leaves after R2, that is being fed back into this system. So that is what we have over here, right? Now, that's my beta circuit. So now if I need to find the beta gain, so beta gain is basically equivalent to okay, just before going into beta gain, you can see IF, or the current in this particular branch across R2 is basically given by I0. I0 is the input current, and then we can use current division. That is, again, if we are finding the current in this particular branch, right, across R2, we have to use the branch opposite to it. So the branch opposite to is R, right? R, and then upon total resistance, that is R plus capital R2. So that is basically equal to your IF. Okay. Now making IF upon I0 the subject of the formula, we rearrange it that will be giving our beta, right? So beta is basically IF upon I naught. In that particular case, that will be equivalent to R upon R2 plus R, right? And then again for your open loop gain, you can say that this IS goes through some gain, right? Some gain that will be mu, and then that gain, I mean, since you're sampling current, that will be across this particular yeah, so basically if you're sampling some, I mean, like you're sampling current. So however, if you do it in terms of the open loop gain as V naught upon IS, right? So whether you sample your output with voltage or current. So in this particular case, they're showing the output, the open loop gain in terms of V naught, right? So V naught is at this particular point upon IS. Actually, it should have been I naught, right? I naught upon IS. That will be the current across this RL, right? However, so if we do V naught upon IS dash, so that is basically going to be some factor mu times R2 plus R, right, into RL plus R parallel with R2. So this, remember, like I said, the open loop gain can be written in multiple factors. However, we are just concerned with the beta second, right? So for this particular tutorial, we are just basically concerned with the beta factor. So in this particular case, our feedback gain is basically equivalent to R upon R2 plus R, right? You can ignore this, right? The alpha variables could be, and the A could be written into multiple variables, right? Okay. Oh, excuse me about that. So yeah. So likewise for the other circuit as well, you can ignore that because we are sampling. In this particular case, we are sampling current, so the open loop gain could be something else as well. However, we are just concerned with the beta gain, right? Beta gain in the beta circuit and how we are able to draw the alpha circuit or the open loop circuit, right? So that was regarding this week's tutorial, right? So if you have any queries, you can ask me, right? So otherwise, we'll end the tutorial over here. So thank you for joining in.